In this video I look at the rules that we use for significant figures and connect that to the idea of propagation of uncertainty. When it comes to the rules, we know we have one set of guidelines when we're doing addition and subtraction, and another set when we're doing multiplication and division. But where do those rules come from, and why are they different from each other? So this takes me back conceptually to think about, well, what is addition? So here I show two different sets. 3 plus 5 equals 8. Now multiplication, 3 times 5. Well, how might I think about that? I guess I could say that I have 3 different sets, each with 5, and that's what totals 15. So both of these, I'm trying to think about how I'm putting together the parts and what the operation of addition means and what the operation of multiplication means. Now, in these examples I just gave, these are with exact numbers. I see precisely 3, precisely 5 to give me precisely 8. There is no uncertainty in those. If I have a measured value, I'm going to have some uncertainty depending on the instrument that I used, the manner in which I made the measurement. So here I showed two different scale readings. If I were to say, well, what do these values tell me? I'm going to try to get as many significant figures as possible. So on that top scale reading, I'm going to call it 2.1. And the second, 4.0. I'm getting as many digits as I'm certain of, and I'm adding one more that I'm estimating. So I could sort of envision, well, what if I put those two segments together? I could see how it would add up to around 6.1. So I have a strong understanding when I'm doing addition of how the place is important. Both of these were being reported to one decimal point, and I can picture in my head as I put those together with those same measuring devices how I could have a value of 6.1 that I would report. There would be uncertainty in that last digit. Now, what if I did the same thing, but I had a different scale rating? In the second one, I'm gonna say the best that I can do is I'm gonna call that a value of 4. It might be a little more than 4, might be a little less, but that's the best that I can estimate that. So if I were to add these two together, I think the best that I could say is it's going to be a value of about 6. I can't have a more precise measurement than that because I can see that this is limiting me to the ones place. Now the way that this shows up, if we want to calculate it in terms of the uncertainty, propagation, how the uncertainty evolves as we're doing different operations, here's our expression that we have from Harvey. So let's say I'm adding 2.1 plus 4.0, I get the value of 6.1. Now within each of those, my understanding is I have an uncertainty of at least plus or minus, let's say 1 in that last digit. So if I'm looking at these, the uncertainty here, I would have a value of plus or minus 1 in 2.1, plus or minus, plus or minus 0.1 in this value, plus or minus 0.1 in this value. And that's what I'm inserting down here. So I would say that the absolute uncertainty I'd have would be 0.1 squared, 0.1 squared. That's coming from each of these. Add those together, take the square root. This is the absolute uncertainty I have. That's the absolute uncertainty when I combine 2.1 plus 4.0, where they each have uncertainty of plus or minus 1 in that last digit. So as I think about this, I would then, with the propagation of uncertainty, report this as 6.1 plus or minus the absolute value, the absolute uncertainty of 0.1. Notice how this guideline right here of our simple rule of reporting it at 6.1, that significant figure rule, it worked pretty well within this one. The simple rule and the more involved propagation of uncertainty when we're adding or subtracting, in both cases said you can report it to one decimal point and there will be uncertainty within that value of around 0.1. So that worked quite well. Now let's look at the other example. So this was 2.1 plus 4. In each of these cases, I'm going to say it's plus or minus 1 in that last digit. So in this case, it would be plus or minus 0.1 for the absolute uncertainty involving the 2.1, plus or minus 1 for the absolute uncertainty regarding this digit 4. Notice how the uncertainty there associated with the value 4 really dominates within that. The absolute uncertainty after I do the calculation is pretty close to the uncertainty that I had just coming from the measured value of 4. So in this case, I would report it as 6 plus or minus that absolute uncertainty of 1. So our rule here, our simple rule of saying report this simply as 6 plus or minus 1, it worked really well again. Now, if I try to think about this for multiplication, it led me to first think, well, what is the operation of multiplication? And the first example that came to mind would be something like area. What is the area? Let's say we're trying to figure out the area of this rectangle shape right here. Well, we know what we would do. We would need two measurements. We would multiply the length times the width. That would get us to the area. And when I say two measurements, we would have two measured values, both of which could have uncertainty, both of which will have uncertainty depending on our measuring device. Now, what's going on here conceptually, it led me to pause and say, well, how does the length times the width get me to the area? Or how does length times width times the height of it, how would that get me to the volume? Conceptually, what's going on? So what I think back to is, what I'm doing is, if I'm thinking about the area, it's as if I'm taking a slice and another slice and another slice and another slice, and this is going to add up to get me the overall area. So I have a certain number of slices and they have a certain size, and that's what I'm combining. That's what I'm thinking about when I'm considering what is the area. Now I could get more advanced than that and thinking about these as being infinitesimally small, and how many of these will I now need to fill up the space. But conceptually, this is what I think is going on when I'm trying to figure out the area. And now how are we going to understand and figure out the uncertainty in an example like this? It's different than just adding together our two parts, because in a way, we don't know how many slices we're going to need. There can be uncertainty in that. And we don't know necessarily the size of the slice. And it turns out within this, when we're doing multiplication or division, we're interested in using the relative uncertainty. So let's look at this example. Let's say 7 times 3, my calculator tells me it's 21. We know that our rule for significant figures would be to report the value as 20 with only one significant figure. How does 21 become 20 in this? Seems like we're losing information. I mean, we could stack it up and say 7 plus 7 plus 7 to get 21. Sure seems like we should be able to report to the ones place. But this right here, this is treating that 3 as an exact number with zero uncertainty. But that's not the case. We don't know that we have 7 precisely 3 times. If we're saying we have both of these as measured values, we have uncertainty in both of those. So we have to do this description here and look at the relative uncertainty. So to solve for the relative uncertainty, let's go back and say this was the digit 7 with an uncertainty of plus or minus 1 in that value. 3 plus or minus 1 in that value. Those would be the smallest amount of uncertainty that I could have. So if I'm looking at the relative uncertainty in each, it would be a value of 1 divided by 7. That will get me the relative uncertainty in this value. 1 divided by 3 gets me the relative uncertainty in this one. I square both, add them together, take the square root of that. That's what this expression is telling me to do. That is solving for the relative uncertainty. Here's the math for that. So the relative uncertainty is about 36%. Most of it is coming from the uncertainty that you'd see involving this digit 3 here. To turn that into the absolute uncertainty, we take the value that we calculated times the relative uncertainty. That gets me the absolute uncertainty. So this would say it's 21 plus or minus that absolute uncertainty. 21 plus or minus about 7. it doesn't make sense to say I can report that to the ones digit. I have a lot of uncertainty relative to that. So instead, our rule says report this as 20. We know that we're confident to the tens place, but we don't have confidence then in the ones place. Because after all, within this value right here, this could be anywhere from 28 to about 14. So that's why our rule says report that value as 20. When I say our rule, the significant figure rules, they're quick approximations for this idea of propagating the uncertainty. And we have different guidelines for whether we're doing addition and subtraction or when we're doing multiplication and division. That much I'm certain of. That much I can see how it leads to different treatments when we have our significant figure rules. And I'm also really confident conceptually for what addition means, because I can see how I'm putting it together and the place is so important. I can see the connection when I'm looking for the relative uncertainty and how that plays a role when I'm multiplying or dividing. But to be honest with you, if you ask me to really say conceptually, what am I doing when I'm calculating the area? My default is to say, well, I'm measuring length times width. Conceptually, I don't go much deeper than that. So I struggle a little bit. Am I simply saying that the rules for significant figures are different because the rules for the propagation of uncertainty are different? I am saying that, and I'm confident that's true. I'm quite confident that I have a good conceptual understanding to see how addition and subtraction work and how the propagation of uncertainty is connected to that. But to be honest with you, I don't know how deeply I can really understand and describe what does it mean to calculate the area. I might have to revisit some elementary school instruction on this. Does elementary school instruction go deeper than telling us what the rule is? If it does, I don't remember it.